We saw in the previous set of videos that an object undergoes oscillatory motion due to a force that is proportional to the displacement of the object and tries to move the object to an equilibrium position. The objects tend to move in a repetitive back and forth fashion about this equilibrium, such as in the case of a mass on a spring, the motion of a pendulum, or vibrations established in a stringed musical instrument. In the latter case, we know that the string vibrates because we can also hear the sound which is being produced. But what do we mean when we say that we can hear the sound produced by the vibration on a medium, and what phenomena are involved in this process? You might have heard that sound is a wave. So what do we mean when we say something is a wave? The most intuitive and easiest wave to imagine is a familiar water wave. Most of us have experienced waves as children when we dropped a pebble into a pond or drops of water into a bucket or glass filled with water. At the point where the pebble or water drops hit the water's surface, waves are created by the impact, which then spread or propagate outwards. Your experience of water waves might also be at the beach, either trying to catch a wave to surf or avoid being knocked by it. A wave is defined as a disturbance that propagates or moves energy from one place to another. So for water waves, the disturbance is the surface of the water, perhaps created by a rock thrown into a pond or a swimmer splashing the surface. For sound waves, the disturbance is a change in air pressure, perhaps created by an oscillating cone inside a speaker or vibration of a string. So it can be observed that wave motion is closely related to the phenomenon of oscillations. Sound waves, earthquake waves, waves on a stretched string, and water waves are called mechanical waves because they propagate through a physical medium. There are other types of waves that do not require a medium to propagate and can travel in a vacuum. These include light or electromagnetic radiation and gravity waves. For now, we'll stick with mechanical waves. The disturbances in a wave are caused by some sort of vibration, and therefore the motion of the medium through which these disturbances are propagating bear a strong resemblance to vibrations found in simple harmonic motion. As such, waves exhibit characteristics common to oscillatory motion, such as amplitude, period, the frequency, and energy. And therefore, wave characteristics can be described by a small subset of the underlying principles introduced in the previous videos. Let's explore these fundamental characteristics of wave motion by considering the case of a simplified string wave. A string wave can be modeled as shown in this animation. As the string section moves up and down, the wave moves in a direction that is horizontal. It looks as though the wave is moving to the right, so the direction of the disturbance and the direction of the waves are perpendicular or transverse to each other. Hence, it is called a transverse wave. This is evident by looking at a single point on the wave, represented by the red dot. You notice that the red dot moves up and down in the vertical direction while the wave moves to the right. The motion of the red dot is simple harmonic. Now let's freeze the wave and have a look at some of its characteristics. The maximum displacement of the disturbance of the wave is called the amplitude. This is the same definition as that for simple harmonic motion. That is, it's the amplitude of the red dot moving in oscillatory motion. The wave traces out a sinusoidal pattern that repeats itself along the direction of propagation. The length of one complete cycle is called the wavelength, and is given by the symbol of the Greek letter lambda. Because the wavelength is a measure of length, it has units of meters. As the red dot oscillates up and down, it does so at a rate given by a frequency of oscillation. The time it takes the red dot to complete one full cycle is the period. The highest point of the wave is called the peak or the crest, and the lowest point is called a trough. And the difference between them is twice the amplitude. As a wave moves linearly to the right, it does so at a given velocity. This velocity is a wave velocity and is determined by the time it takes the wave to propagate one full wavelength. So the wave velocity is defined as a wavelength divided by the period. Since period is the inverse of frequency, then the wave velocity can also be written as a product of the frequency and the wavelength. This definition is true for all waves. It should be noted that the wave velocity is different to the velocity of the red dot, which represents the wave particle. The red dot moves with varying velocity, which we previously defined in the simple harmonic oscillation videos. So the velocity of the particle that has been disturbed, as shown by the velocity vector here, is different to the velocity of the wave. One varies and changes directions as a function of time, while the other is constant and moves in one direction. Which velocity is constant and moves in one direction? If the wavelength of this wave is 10 meters and the period of oscillation is 5 seconds, then what is the speed of this wave? Another type of mechanical wave occurs when the particles in the medium are disturbed along the same direction as the direction of the wave. These waves are called longitudinal waves. Examples of longitudinal waves include slinkies and sound waves. The following provides an animated illustration of a longitudinal wave. Observe the red bar, which represents a particle in the medium that the wave is propagating through. It looks as though the wave is moving to the right, but the particle itself is oscillating back and forth in the horizontal direction in simple harmonic motion. This is more evident when we plot the motion of the particle as a function of time. We can see that it traces out a sine wave. So all of the properties previously described apply. That is, the wave has an amplitude, a frequency, a period, and a wavelength. In a longitudinal wave, there are no peaks and troughs because the disturbance is not perpendicular to the wave direction. Instead, there are regions where the wave particles are close together or compressed. For this reason, the longitudinal waves are also called compression waves. Regions of compressions in a wave are more dense. In between two compressions are regions where the particles are spread out. These regions are called refractions, and they have less density. The distance between two successive compressions or refractions represents the wavelength of a longitudinal wave. It can be seen in the example in the transverse and longitudinal waves that the particles that create the wave oscillate about its equilibrium position in one location while the wave moves. The movement of the particles causes the wave, and the movement of the wave transfers energy. In summary, a wave is a disturbance that moves energy from one point to another. A wave has a wavelength, which is a distance between adjacent identical parts of the wave. The particles in the medium move in oscillatory motion. The disturbance is what causes a wave, and the wave moves with a linear velocity. The velocity of the wave is given by the ratio of the wavelength to its period, or the product of its frequency and the wavelength. A transverse wave is a disturbance that is perpendicular to its direction of propagation, whereas a longitudinal wave has a disturbance that is parallel to the direction of propagation.